is about our concern. Left figure is a system chart. Please see figure for details. The feature of our concern is a tire mechanism and a separation mechanism. All components are installed inside of tire system. This mechanism assures rover will run over loop in the desert. Parachute ropes are tire separation mechanism. Rover can start to run without setting twist to rope. The details are as follows. The first try, the result was failure. Failure pattern is freefall. Because the separation mechanism had been damaged by the impact of the parachute deployment. Next, the second try result was failure. Our concern didn't run after landing because the motor was probably a poor contact. Also, we were not able to take a photograph. We have satisfied pretty much the team has participated in ARLISS. Thank you for development member and everyone. That's all.
Good morning, everybody. I'm representing the University of Hawaii Windward Community Campus team. We competed in the ARLISS comeback mission. So the basic goal was to reach within 10 meters of the target while recording some sort of atmospheric data. Okay, so we chose to do a flyback vehicle. We did not have any ground traverse abilities. So some of the challenges with this design is that we have to fly to the target. If we come up short, there's no way of reaching the target at that point. So, and then of course an obvious concern with that is battling headwinds. We're uncertain of the wind conditions, the wind speeds up at higher altitudes. We kind of have a good idea of what they are at the ground level, but they could be much higher when we get up to 2 miles. And also, what's proven to be quite a problem in the past is having a mid-descent deployment of our parasite. So to answer those challenges, what we decided to do is incorporate what we call a rapid descent phase, and this is our payload project here. And the rapid descent phase is exactly how you see it here. There's no parasail deployed at this point. And the purpose of this is to fall quickly and get into head in the general direction of the target. And basically so that we don't get carried away by the headwinds. If we were to deploy our parachute or our parasail at apogee, we might just get blown away from the target. So we have a rapid descent phase. The steering in this phase is controlled by our steering ring here on the back, connected to a servo on the inside. And then at that point, at a desired altitude, it changed from flight to flight depending on what we thought the wind conditions were. We deployed the parasail at a lower altitude, for example, like 1,100 feet. And a charge, kind of like how a rocket does its deployment, black powder charge flows our parasail out the back end, and at that point we are in the gliding descent phase, and there we can do some more fine tuning with the direction changes. We have a lot more control of the vehicle at that point. This was controlled by the deployment of this was controlled by our Raven 2 flight controller, and that's what deployed the parasail. So just a basic run through of what we have in here. We have a GPS flight ST900 unit. This is separate. This is a separate GPS unit from what's controlling our controller board. Basically, what's doing the steering. This is strictly for ground trace for us on the ground, since our controller board doesn't have a transceiver on. So we use the parallax propeller protocol board with the temperature sensor for our controlling unit, and we had hooked up to that one servo and parallax GPS antenna. Okay, so this is our first flight, the results from our first flight. We had landed about 161 meters from the target. And, this is the picture of exactly where he landed. You can see where it impacted the soil. In the background, you can actually see the flag, the target. And unfortunately, since I didn't have internet connection, I couldn't load any background maps or dress this up too much. But this was our ground trace from the flight. The line starting on the bottom left is where the takeoff point was. At that point, it ascended upwards. We lost trace momentarily, but then it picked back up. The kind of sharp angle at the top there, that's when the rocket's parachutes deployed. And then we had a slight delay until this was deployed, 6 to 8 seconds. And then at that point, you can see that it goes through its rapid descent phase, the relatively straight line facing downwards, and it kind of gets it into the general area of the target. When our parasail was deployed, because of the angle of the parasail, we started drifting away from the target. The target is the red dot. And it had eventually turned itself around and headed toward the target. And unfortunately, we didn't land as we were passing the target. We flew past the target. It started turning itself around. The line kind of arcing away from it is probably getting caught in a little bit of wind. Started drifting away, but it turned itself around again and started heading back. And we landed at the green point marked by the 001. So that was approximately 161 meters away from the target. This was our first flight. On our second flight, I don't have a slide on it for here, but we had deployed the chute because of heavy winds at a lower altitude, and we unfortunately could not, we did not have enough glide time to get ourselves to the target, so we touched down on our second flight roughly about 1 mile away from the target. This is the uncalibrated temperature data. So just showing the temperature data we got. The prep area was in the stage, so once we had assembled everything, the electronics got turned on, the plummeter starts to heat up itself, so you can see the temperature increase. And then especially when it goes onto the pad and is sitting in the sun, it's going to heat up. And upon deployment at the end there, you can see a sharp temperature drop. Okay, we'd like to give a special thanks to Hawaii Space Grant Consortium. That's our funding agency that allowed us to get out here. Of course, our mentor, Dr. Jacob Hudson, and Jim and Becky Green. Without them, none of this would have been possible. We ship everything to them. Of course, Aeropat for hosting everything. Thank you.
Fusion Institute of Technology. So I will talk about our report. I will talk about the report of our concept mission. So first, I will talk about our sequence in ARLISS. So first, our concept descent by parachute, and after that, about 30 seconds, separate the parachute and open the purport. So start the automatic flight by parachute purport. So our concept is shown in this figure, and the table shows detail of our concept. So right figure shows top view of our concept. Our concept has 3 pitot tubes, so it can fly with measuring airspeed and air direction. So this is the result of first upper figure. Upper figure is result of first flight. So separating parachute is success, but these tackle components was broken by parachute opening shock because Because of this, our concept was not able to control. And under picture is the result of third branch. Separating parachute is successful and the components withstand the opening shock. But the line of performance was very twisted. So our concept was not able to control again. These figures are result of second and fourth flight. So these in both of these cases, our concept pursuit was not spied, so concept was not able to control it. As mentioned above, our concept has 3 pitot tubes. These data are output of each tube. So I'm sorry, these data are under analyzing, but maybe over 15 meters per sec wind. So too strong. Be careful in next year. So these are our results over there. Thank you for listening and thank you for great lunch for Airpacks. That's all. Thank you.
My presentation on behalf of the University of Tokyo, undergraduate team and April 11. If anything is unclear during my presentation, I'll be glad to reply all of your questions after my presentation. So let's begin. First, we'll explain the structure. Now, let's have the top-bottom structure here. We'll firstly explain the packing and release. And to explain this, we'll demonstrate actually. And firstly, the rocket is launched, and our cancer got about 4 kilometers from the ground, and will release. You got it. I like this. We'll release our concept. And we move into the overall structure with this actual body. Our concepts and main wings and tail wings are basically made of the retractable measuring tapes and plastic folders. I like this. Yeah. And then this part, these individual parts are basically fixed with metal wires and glass tapes. And then the question, when a nurse, how much do you think our concept weighs? What do you think? The answer is 563 grams. Yeah. If you do you think it's a very nothing or very light? It's a bit heavy for our type and wing type of concept. But it's really heavy. But with this with this weight, we can realize the 15 meters per second of our concept speed, 55 meters per second. And we move on to the result. And for our first flight, was the second day of the ARLISS, and our result was weather. Our concept falls down and almost vertically, and it's because our flat fins were not activated because of our weather of structure. We ended to landing about 1,100 meters away from the target. Then we developed our bodies furthermore, and we measured that to the second flight and towards second flight. And the result of the second flight, the last day of the ARLISS, was also failure. We failed again, and this time it's because that GPS data wasn't gotten, so we couldn't control decently our concept, and we ended up landing on the point 655 from the exact target. For board flight, we couldn't get any of the actual data, such as GPS data or location data, or so on. And finally, I want to say really thanks to all launchers of our concept, especially for Alan for our first flight, then for the second flight, and Bob, and thanks very much. And thank you all for them, and also the Aeropack and members, and that's it.
Okay. Hello everyone. Then I will start Team Octane's presentation. First of all, we tried two missions. One is Korekiyo and the other is Echizen. Then, first, I will present Korekiyo missions. Korekiyo is a satellite relates GPS data of the transmitters to the central ground station. In this mission, we placed transmitters in various places in the desert, and the transmitters transmit its GPS data to the CANSAT, and CANSAT collects the GPS data from several different ground transmitters, and CANSAT relates those GPS data to the central ground station to inform their coordinates. I think this system can be connected to the various practical applications. One is disaster relief activity like this, and next is our goal of this mission in the future, prevention loss of concepts. We would like to equip the transmitter into its team's concept so that we can know the place of its concept. Then it is useful for prevent loss of any concepts. Then I will explain Korekiyo's success criteria. Minimum success is the concept collects the GPS data of at least one transmitter, and the data is linked to the ground station. And full success is the concept collects the GPS data of at least two transmitters, which are 4 kilometers distant from each other, and the data is downlinked to the ground station. And the other is at least one transmitter survives for more than 24 hours. Then I will explain Korekiyo's system overview. This concept has very simple system, only mainboard, GPS, transceiver, SD card, backpin, and battery. And the transmitter is very small. The largest is 31 millimeters, can be equipped into the concept. We placed 3 transmitters as a regular triangle. The distance between the transmitter is about 4.2 kilometers.